So let's start with our first chapter of class 11, that is some basic concepts of chemistry. So the first concept in this chapter is about matter. Matter is anything that has mass and occupies space, as we know. Next, learning about classification of matter. Classification of matter, it can be made in two types, that is physical and chemical. Okay, in physical we have solid, liquid, gas, plasma and BEC, that is Bose-Einstein condensate. These two, plasma and Bose-Einstein condensate, we learned in our high school classes. Coming to chemical. Chemical classification of matter includes two more types, that is pure substances and mixtures. So pure substances are of again two types, elements and compounds. Simple example of elements can be oxygen, nitrogen and fluorine, chlorine, etc. Coming to compounds, compounds are of two types, organic compounds and inorganic compounds. Organic compounds are compounds which are found in living sources or which are obtained from living sources, while inorganic compounds are the compounds made in laboratories. Now coming to mixtures. In mixtures, there are two types of mixtures, homogeneous mixtures and heterogeneous mixtures. The word homo means same. Same in molecular structures. Means what? Homogeneous means the type of mixtures which have same composition throughout the solution. Heterogeneous mixtures are mixtures which do not have same composition throughout the solution. Hetero means different, different composition. Now, a simple example for homogeneous can be salt and water. Okay, when you dissolve salt in water, it fully gets dissolved, and in each and every drop of that water, you will get salt taste. It is called homogeneity. Now, coming to heterogeneous mixture, if you add mud into water, it will not get mixed. Right? In each and every drop of water, you will not be able to find mud. Okay? Now, coming to, okay, so these all definitions were clear. Now the third topic and the second topic. The both topics are firstly conversions. Learning about the basic conversions. Those are, firstly, while converting gas to liquid, this process is known as condensation. Water vapor converting into water, it is known as condensation. Water to ice is known as freezing. Ice to water vapor, which is not possible in water, but it is possible in other substances. For example, naphthalene. Okay, it can convert directly from solid to gases. It is known as sublimation. Now coming to the reverse process, from gaseous state to solid state, this process is known as deposition. From solid state to liquid state, this process is known as melting. From liquid to gas, it is known as vaporization. We can remember it like water converting into water vapor. It is known as vaporization. Now coming to some basic unit conversions. So these all things which we are learning in this first chapter will help us throughout the whole chemistry of class 11. So the first is length. In length, 1 mile is equal to 1760 yards, which can also be written as 1.6 kilometers. 1 yard is equal to 3 feet. 1 foot is equal to 12 inches. These are all the basic things you should know. 1 inch is equal to 2.54 centimeter. The second is mass. In mass, 1 ton is equal to 1000 kg. 1 quintal, it's Quintal, quintal is equal to 100 kgs. So in these usually we get confused, ton and quintal. Okay, so 1 kg is equal to 1000 gram. As we know, 1 gram is equal to 1000 milligrams. 1 AMU, that is 1 atomic mass unit. 1 atomic mass unit is equal to 1.6 into 10 to the power minus 24 grams. Similarly, if I want to write in kg, I will divide it by 1000, that is to the power 10 to the power minus 3. So 1 atomic mass unit can also be written in the form of 1.67 into 10 to the power minus 27 kg. Then the third one is temperature. Temperature, first conversion is Celsius, degree Celsius to degrees Fahrenheit. Now, degrees Fahrenheit can be obtained by 9 by 5 into degrees Celsius plus 32. This is the formula. Coming to the next formula for obtaining degrees Celsius from degrees Fahrenheit. Okay, so degrees Celsius is equal to 5 by 9 into degrees Fahrenheit minus 32. Okay, just the reverse of this formula. Okay, 9 by 5, 5 by 9 plus 32 minus 32. Now, coming to degrees Celsius to Kelvin. Okay, Kelvin is equal to Celsius plus 273, this number. Okay, similarly, Kelvin to Celsius. Celsius is equal to Kelvin minus 273, that is take this 273 that side. Okay, for example, if I want 0 degrees Celsius, it is 273 Kelvin. Okay, similarly, if I take 0 degrees Fahrenheit, okay, in terms of Fahrenheit if I take, then it would be 0 degrees Fahrenheit, that is this whole term becomes 0. So in Celsius it is minus 32 degree Celsius. Coming to energy. Energy, 1 calorie is equal to 4.18 joules in proper numbers, which can be taken as round off as 4.2 joules. 1 electron volt, EV is electron volt, is 1.6 into 10 to the power minus 19 joules, and 1 joule can be written as 10 to the power 7 ergs, ERGS. Now 1 liter ATM can be written as 101.3 joules. Coming to pressure, 1 ATM is equal to 0.987 bar in proper numbers. If you want it, we can round it off to 1 bar. 1 ATM is equal to 1 bar. 1 ATM can also be written in the form of 760 torr, TORR, torr. Okay, which can again be written as 76 centimeter of Hg. Now, 1 ATM can again be written in the form of pascals. Okay, because it is pressure, right? In our lower grades, we learned that the SI unit of pressure is pascals, right? So, pascals, in terms of pascals, 1 ATM is equal to 1.01325 into 10 to the power 5 pascals, or simply 101,325 pascals. And pascals, as we know, is force upon area. Pressure is force upon area. So, force is Newton upon area. Okay, area is meter square, SI units. Okay, so 1 pascal can be written as 1 Newton meter raised to minus 2, that is Newton per meter square. Similarly, 1 ATM can be written in the form of 101,325 Newton meter raised to minus 2. Now we are done with the unit conversions. So now coming to the laws of chemical combination. So there are total 5 laws. Firstly, let's discuss the law of conservation of mass. So this is a very common law that we have discussed in our lower classes as well. So this law is given by Antony Lavoisier. Okay. So the law states that mass can neither be created nor destroyed, but it can change from one form to another. Okay. For example, let's take an example of a simple reaction, that is formation of ammonia. Okay. That is N2. Okay, N2 is nitrogen molecule. Okay, N2 plus 3H2 gives NH3. It will give 2NH3. Okay, balancing the reaction, 2 nitrogen, 3 2s are 6 hydrogen, 3 2s are 6 hydrogen. Okay, so here calculating the mass of nitrogen in N2. Okay, N2 molecule has weight of 28 gram per mole. How did I know it? See, for 1 nitrogen, we have the atomic number as 7, right? Atomic number as 7. Now, atomic number is the number of electrons. So, therefore, the weight is 14. Number of electrons plus protons. Actually, it's the number of protons plus neutrons. Okay? So, the weight is 14 for 1 electron, for 1 nitrogen. Here we have 2 nitrogen, that is 2 into 14, which is 28 gram per mole. Okay, gram per mole. Now coming to H2. Now the weight of 1 hydrogen atom is 1. So here we have 6 atoms like that, right? 6 hydrogens we have, so 6 gram per mole. Now if I add these two, what I will get? I will get 34 gram per mole on the reactant side, right? 34 gram per mole on the reactant I check, sorry, here for again N it is 14, for again H it is 1, but here 3 hydrogen are there, so 3 plus 3, what I get 17, again 2 moles of NH3, right, so into 2, so 14 plus 3 is 17, into 2 is 34, so again you got 34 gram per mole on the product side as well as the reactant side. Okay. Now coming to the next law, which is law of definite proportions. It is given by Joseph Proust. So this law states that a given compound always contains exactly the same proportions of elements by weight. Now what does this mean? This means that if I take a simple example of water, that is H2O. Okay. So whether it be tap water or river water or rain water, it would be in the form of H2O only, right? That is taking H2O. Okay. So here atomic mass of hydrogen is 2, right? 1 into 2, that is 2 is 2, and then the ratio for 1 oxygen the atomic mass is 16. Okay, so it would be in the same ratio, that is 2 is to 16 by weight, that is atomic weight. Okay, atomic mass. Okay, so this same H2O molecule will be present in river water, or it will be rain water, or it would be anything, right? Any source of water. Now coming to the third law, that is the law of multiple proportions given by John Dalton. So if two elements can combine to form more than one compound, for example carbon and oxygen, right? If I combine those two, I can get carbon dioxide as well, I can get carbon monoxide as well, right? CO is carbon monoxide, right? While CO2 is carbon dioxide. Okay, so if they combine to form more than one compound, then the masses of one element that combined with the fixed mass of other element are in the ratio of small whole numbers. So this of course needs an explanation. So after this, knowing the statement, we'll come to the explanation. The examples for the same of the law of multiple proportions are, as we discussed, C plus O giving CO as well as CO2. So here as you can see, we talked about fixed mass in the definition, right? So here the fixed mass is of carbon, that is 12 and 12. Okay, 12 gram per mole. Okay, so here the changing mass is oxygen, right? And it is the same element acting with both the carbons, right? But in the form of 1:2 ratio. So the law was that the elements react with the fixed mass in the form of whole numbers, right? In the form of whole numbers. So 1:2 is whole numbers, simple whole numbers. Similarly, we have for N plus O, that is N plus O. Okay, so why did I take 2? Because in all the cases, as you can see, we have 2 nitrogen. So I took 2 nitrogen and 2 oxygen here. So 2 nitrogen plus 2 oxygen, as you can see here, we will get N2O. Here same nitrogen and oxygen reacting, and here the fixed masses of nitrogen, as you can see, 28, 28. In all the compounds it's 28 only. Okay, and the changing masses of oxygen. Okay, so oxygen also, it is in constant mass, and the ratio of atoms or the weight of oxygen is in the form of simple whole numbers, that is 1:2:3:4:5, that is 16, 32, 48, 64 and 80. Okay, these are in simple ratios. Okay, now coming to the next law given by Gay-Lussac. When gases combine or are produced in a chemical reaction, that is the short form for reaction, when they are produced in a chemical reaction, they do so in simple ratios, provided all the gases are in same temperature and same pressure. So here, this is the example, that is 2H2 plus O2 giving 2H2O. Okay, so gases combine in simple ratios, that is 2:1. As you can see, here we are just considering this coefficient. Okay, 2:1 ratio. Okay, they combine in 2:1 ratio when same temperature, when these two are in same temperature and at same pressure. Now coming to the last law, that is Avogadro's law. We know about Avogadro's constant also, but now we are studying about Avogadro's law. that is equal volumes of all the gases contain the same number of molecules at same temperature and pressure. Okay, so this was the last law of laws of chemical combination. Now coming to some basic definitions that we need to learn for our further chemistry lessons. So first is relative atomic mass. So relative atomic mass, we can obtain it by the formula. So the first word is relative, means we are going to relate it with something. What is that something? That is mass of C12 atom. So C12, that is carbon 12, carbon with atomic mass 12 is considered a standard atom in chemistry. Okay, so the relative mass of an element in comparison with 1/12 of the mass of the C12 atom, carbon C12 atom. Okay, so we can derive a formula from this. Mass of one atom of an element, one atom of an element means what? Now the total number of nucleons into mass of nucleons, right? So for example, hydrogen, if I have, so in hydrogen, okay, or let's take the next element, that is helium. So in helium we have 2 protons and 2 nucleons, right? Similarly 2 electrons. So total we have 2 neutrons and 2 protons, that is 4 nucleons. So number of nucleons is 4. Mass of one nucleon, that is mass of one proton or the mass of one neutron. Okay, that many times the mass into 4 times, right? So that mass is the total mass of an atom. Okay, number of nucleons, that is number of protons plus number of neutrons, and into the mass of one nucleon, that is mass of one proton or mass of one neutron, divided by 1/12 into 12 times mass of one nucleon. Why did we take 12 2 times? Because first of all, in the first equation we had 1/12, we took 1/12. Now mass of one C12 carbon atom, again we have mass of an atom which is 12, which means that it has 6 protons and 6 neutrons. 6 neutrons, 6 protons, together 12 nucleons, that is the number of nucleons into mass of one nucleon. So here, as you know, we can cancel out mass of one nucleon, mass of one nucleon. So we'll get, and 12 cancelled out. So the RAM, which is relative atomic mass, is equal to the total mass of nucleons. That is the total number of nucleons. Okay, total number of nucleons. For example, if I take it for simple helium, He. Okay, so total number of nucleons is 4. So the relative atomic mass is 4. Okay, simple. Now coming to next, atomic mass unit, AMU. Okay, so we also saw it before while learning basic conversions. So 1 AMU is 1/12 of the mass of one carbon C12 atom. Okay, so 1 AMU, again I can write it as mass of one nucleon. Why? Because mass of one C12 atom means what? 12 into mass of one nucleon. Again 12 will get cancelled like this. So we will get mass of one nucleon remaining. So mass of one nucleon is what is 1 AMU, that is atomic mass unit. So 1 atomic mass unit is equal to 1.67 into 10 to the power minus 24 grams. This is grams. Again if I take in kg, it would be 10 to the power minus 27 kg. Okay, coming to atomic mass. So atomic mass, as we know, it is the total mass of an atom, right? For example, it is the total number of nucleons, right? Total number of nucleons is known as atomic mass. For example, for nitrogen, as we discussed, it is 14, that is 7 protons, 7 neutrons. It is 14 for nitrogen. Okay. For similarly, that atomic mass, we can get one more formula with the help of our relative atomic mass and atomic mass unit. That is, relative atomic mass is equal to the atomic mass of an element, okay, divided by AMU, that is the atomic mass unit. So therefore, from this formula we obtain the formula for atomic mass, that is RAM, that is relative atomic mass, into the second point that we studied, that is AMU. Now coming to mole concept. So what is mole? Any number of entities of a substance is known as moles. What is Na? That is Avogadro's constant, 6.022 into 10 to the power 23. This is very important. Okay. So any number of entities. What is entities here? Entities may be atoms, it may be molecules, right? Yeah, it may be molecules, atoms, anything. Okay. So Na, that is 6.022 into 10 to the power 23 number of atoms or the same number of molecules are known as moles. Okay. Now coming to gram atomic mass. What is gram atomic mass? It is as simple as that. See, atomic mass that we got it over here into Na, that is Avogadro's constant again. Okay. Coming to molecule. What is molecule? Molecule is a substance with more than one element. Okay. For example, HCl molecule. Okay. Hydrogen chloride. Okay. Or hydrochloric acid. Now coming to the next one, that is molecular mass. Molecular masses, here we learn atomic mass. Okay, mass of one atom. Okay, here it is molecular mass of one molecule. Okay, which is mass of molecule in atomic mass units. Coming to the last one, that is gram molecular mass. Here we learned gram atomic mass. Now we are learning gram molecular mass. The only difference is in gram atomic mass we will multiply Na with atomic mass. Gram molecular mass we will multiply Na with molecular mass. Okay. So we are done with the basic definitions that we need. Now coming to the Y-map of mole concept. So here this Y-map tells us about three formulae of calculating moles. So the first formula was like volume of the element or volume of the molecule divided by given volume by molar volume, that is 22.4 liter. Second is given weight by molecular weight, and the third one is number of entities about divided by Na, that is Avogadro's constant. So this Y-map is very important for calculating number of moles. So the next topic is percentage composition. So finding the percentage of each element in a compound is known as percentage composition. So how can we find it? This is the formula. That is atomic weight into number of atoms. Okay, divide atomic weight of that element for which we want to find the percentage composition. Okay, so atomic weight of that element into number of atoms of that element in the compound. Okay, divided by molecular weight of the whole compound into 100 because it is percentage. Okay, for example, let us find out the percentage composition of each of the elements in CaCO3, that is calcium carbonate. Okay, so the molecular weight of calcium carbonate is 100. How did I get it? Calcium molecular weight, atomic weight is 40. Okay, for carbon it's 12, and for each oxygen it's 16. O3 it's there, right? So 3 into 16, that is 48. Okay, so here you will get 60 plus 40, that is 100. Okay, now percentage composition of calcium. What I have to do? Atomic weight, that is atomic weight of calcium is 40. Okay, into the number of atoms, into one atom of calcium is there. Now divided by molecular weight of the whole compound, that is 100 into 100 because I want percentage, right? So this will be equal to 40%. Okay, so 40% of the whole compound is calcium. Coming to the next one, carbon. Okay, molecular weight, atomic weight of carbon is 12 into how many atoms of carbon are there? 1 divided by what we will get? 100, right? Molecular weight of the compound into 100, again 12%. Okay, similarly for oxygen, 3 atoms of, firstly atomic weight of oxygen is 16 into 3 atoms of oxygen divided by 100, that is the molecular weight of the compound. We will get 40 8%. So like this you need to find the percentage composition of each and every element of a given compound. Now coming to density. So density is of two types, absolute density and relative density. As the name suggests, absolute density is the density of its own single element or single compound, whereas relative density is density in comparison. Okay, so case 1, solids and liquids. For solids and liquids, absolute density is mass by volume, mass in grams, volume in ml. Therefore the unit is gram per ml. Okay, whereas the relative density RD is density of the substance or density of the element or compound which I have divided by density of H2O, that is water, at 4 degrees Celsius. So this is a unitless quantity because density by density units will get cancelled. Okay, now coming to second, that is gases. Case 2 for gases, absolute density, we will find the absolute density in the following steps. PV is equal to nRT. This is called ideal gas equation. Okay, so where P is pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is the temperature. And also you need to remember the units for the same. P, that is pressure, is in atm. Okay, pressure is in atm, volume is in liter. Okay, number of moles, it's in numbers only, it's unitless quantity. While R is universal gas constant. Okay, so universal gas constant has 3 values according to its units. So universal gas constant has 3 values, that is the first value is 8.314. Okay, this is in joules, while the second value is 0.0821. The third value is 2, this is in calories. Okay, so now coming to T, that is temperature in Kelvin. Okay, next from this number of moles, we had a formula for number of moles, that is given weight by molecular weight, right? So we applied that formula here, we got W by mW into RT. Now I will replace this V with this mW, that is I will take mW that side, I will take V on the right hand side. Now I will get PM is equal to given weight by given volume into RT. Now what is weight by volume? Mass by volume is density, right? So we will get density. Okay, PM is equal to density into RT. So density I can write as PM divided by RT. So this is our formula for absolute density in the case of gases. Now coming to relative density, it is the same, that is here with the formula we can see that density is directly proportional to mass, right? Mass of the gas, molecular weight or atomic weight, right? So D is directly proportional to M. Therefore D1 by D2, that is relative density of the two gases, is equal to M1 by M2, that is the relative masses of the two gases. Now coming to vapor density. Vapor density is what? Again we will take the same one, D1 by D2 is equal to M1 by M2. While here vapor, the word comes, so we will take it as water vapor, right? So that is H2O. But here the gas is H2, not H2O. Okay? So the vapor density means that mass of first gas divided by mass of H2. H2 gas is having the mass of 2. So we can directly write vapor density as it is the mass of the given gas divided by 2. Okay? So the 3 values of R have respectively these units, that is first is 8.314 joule per mole per Kelvin. One more value is 0.0821 liter atm divided by mole per Kelvin. And third one is 2 calories per mole per Kelvin. The next topic is calculating average atomic weights for isotopes. So isotopes are the substances which are of the same element, okay, but they have different atomic weights. Okay, they have the same atomic number but different atomic weights, which means that they have same number of protons but the number of neutrons is different. Okay, so now finding the average atomic weight for isotopes. Let's understand this with the help of a question for chlorine. Okay, so chlorine is found in two types in nature, or two isotopes in nature. Okay, so the first A is for percentage abundance, which means that 75% in environment, 75% of chlorine found is of the form Cl35. 35 is atomic weight. Okay, so Cl35 type of chlorine or isotope of chlorine is found in 75% in the environment. Okay, similarly 25% of chlorine found in the environment is of the type Cl37, chlorine with the atomic weight 37. So how to calculate average atomic weight? You can calculate it with the formula like this, that is A1 into AW1, that is abundance, percentage abundance. Okay, it is given in percentage abundance into atomic weight of the first element, of the first isotope, plus again percentage abundance plus atomic weight of the second isotope, and so on. If you have as many isotopes, you have to do in the same manner, divided by 100. Okay, so let's calculate for this, that is A1 into AW, that is 75 into 35 plus 25 into 37, okay, into 37. So we will get the whole divided by 100. Okay, so after multiplying and dividing, multiplying and adding, okay, so we will get 3550 divided by 100, that is 35.5 gram per mole is the average atomic weight of a Cl chlorine atom. Okay, it is the average atomic weight for all isotopes of chlorine. Okay, so similarly you can find for other atoms as well, or other isotopes of elements as well. Now coming to the next thing, that is limiting reagent. So what is a limiting reagent? The reactant which is consumed first in a reaction is called limiting reagent. Okay, which sacrifices itself or is consumed first is known as a limiting reagent. Okay, now how to find the limiting reagent? So let's understand this with an example or with a question. Okay, so the question is, find limiting reagent of if 3 moles of A, that is 3 moles of A react with 9 moles of B to give the following reaction. Okay, this reaction is given in the question. Okay, so this is the formula for finding limiting reagent, but how to use it and how to find the limiting reagent? See, first is the number of moles. Let's find for A first of all. Okay, number of moles of A is 3. Now what is stoichiometric coefficient? Stoichiometric coefficient means the coefficient that is present beside the element. Okay, the coefficient that we use while balancing. Okay, so here the coefficient is 1, right? 3 by 1. So A has 3. Okay, now for B if I take, okay, for B when I take, it is 9 moles, number of moles is given 9 and divided by 2, that is stoichiometric coefficient. Okay, so I get here 4.5, right? So A has lesser value than B, therefore A gets consumed first and A is the limiting reagent. So like this you have to find the limiting reagent of a reaction. So the next topic is stoichiometry. So stoichiometry is just describing a reaction in different ways. Okay, for example, let's see this reaction, that is CH4, that is methane plus oxygen gives carbon dioxide plus H2O. That the reaction is known as combustion of methane. Okay, combustion, burning methane in the presence of air, that is oxygen. Okay, so this reaction can be expressed in 4 forms, that is in the form of moles. Firstly, that is 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of CO2 and 1 mole of H2O. Okay, this was in the form of moles. Okay, so there should be 2 as per balancing. Okay, so 1 mole of methane on reacting with or reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water or H2O. Now a second thing. Second, we'll talk in the terms of weight. Okay. So for methane, I'll find out the molecular weight. C is 12 plus each hydrogen 4, 16 grams. Okay. So 16 grams of methane on reacting with 2 2s are 4, 64 grams of oxygen. Okay. 16 grams of methane on reacting with 64 grams of oxygen will give me 44 grams of carbon dioxide. You can calculate 12 plus this is 16 2s are 32. Okay, 44 grams of oxygen and plus 36 grams of H2O. Okay, so this was in the terms of weight. Now coming to in form of molecule. Okay, so we can say Na molecules, that is Avogadro's constant. Na molecules of methane reacting with 2 Na molecules of oxygen will give me Na molecules of carbon dioxide plus 2 times or 2 Na molecules of water or H2O. Okay, in terms of volume, if we talk about volume, molar volume, that is 22.4 liter. Okay, so for 1 mole, right? So again, wherever I wrote 1 mole, I write 22.4 liter, that is 22.4 liters of methane on reacting with 22 into 4, that is 44.8 liters of oxygen will give me 22.4 liters of carbon dioxide plus 44.8 liters of water or H2O. So this easy was stoichiometry. Now coming to finding out the empirical and molecular formula with the help of given molecular mass. Means, what is the meaning of this? 3 percentages are given to you, percentage compositions, that is carbon 40.6, hydrogen 5% and oxygen 54.4%. From these 3 informations and also molecular mass of the whole compound is given 118 gram per mole. From these 4 points we need to find the formula of that compound. So it is very easy, it just needs 1, 2, 3, 4, 5, 6 columns. Okay. So after drawing these 6 columns, name them as element, percentage composition, atomic weight, percentage composition divided by atomic weight, simple ratio and simplest whole number ratio. Okay. So next we'll write down the elements, that is carbon, hydrogen, oxygen. Okay. So the next step, write down the percentage composition. Whatever is given, we'll write down. Okay, that is 40.6, 5 percentage. Okay, this is H, and this is 54.4 percentage. Okay. Now coming to atomic weights, we should know the atomic weights of elements. Carbon is 12, hydrogen is 1, oxygen is 16. Okay, so these all should be learnt. Now coming to division, 40.6 divided by 12. This is 40.6 by 12. You can directly write down the answers as well. Okay. So here I'll directly write down the answers. Okay. So here I'll get the value as 3.88. Okay. Now next, 5 divided by 1, 5 itself. 54.4 divided by 16. I'll get 3.8. Or perfection value if we want, I'll get some around 3.4. Okay. So now simplest ratio. Simplest ratio in the sense, we'll divide this. What is the smallest number we got here? We got the smallest number as, we'll round it off to 3.8 itself. Okay, because these numbers will match them. So we got the smallest number 3.88. We'll divide everything by 3.88 itself. Dividing 3.88 by itself, we'll get 1. 5 divided by 3.88, we will get 1.47, which can also be written as 1.5. Okay. Again, I will divide 3.8 divided by 3.88, that is, I will get 1.09 something. I can round it off and write it as 1. Okay. So here, simplest whole number ratio, this is a very important point you need to listen. Here, simplest whole number ratio, here I am getting 1.5, right? If I get something in terms of 0.5, then only I need to multiply all the ratios with 2. Why? Because I want whole number ratio, right? Here I will multiply everything by 2. Okay, all the ratios by 2. I will get the ratio 2:3:2. Okay, you understood? If we did not get any of the ratios in the form of 0.5, 1.5, 2.5, whether it be anything, okay, so we will not multiply with 2. Here I got it 1.5, so I am multiplying it with 2. So now the empirical formula, okay, empirical formula, we got it as, we will use these with C, H and O. We got C2, H3 and O2. C2H3O2. This is the empirical formula. Now how can we get the molecular formula? First of all, molecular formula can be written as empirical formula to the base n. To the base n means that multiplying these values. Okay. So how should we find n? Right. So n has one more formula, that is, here n does not mean number of moles. It is to the power n, which means that it is the coefficient that we will multiply. Okay. So the formula for this n is molecular weight by empirical weight. Molecular weight of this you need to find. Carbon 2 times 24 plus hydrogen 3 times 3, oxygen 2 times 16 2s are 32. So you will get the molecular weight as 24 plus 3, that is 27, plus 2 29, plus 3 plus 30 is 59. We will get 59. Okay. So it should be actually empirical, yeah. Empirical weight by molecular, no, it should be, yeah, it should be molecular weight by empirical weight. As we did earlier, empirical weight I got at 59, molecular weight is given in the question, that is 118. Right, so 118 by 59, what is the answer? It's a perfect 2. Right, so this n factor is 2 now. So we got our molecular formula as the whole into 2, that is C4 multiplying by 2, okay, H6O4. So this is our molecular formula. In this way we will find molecular formula. Now we come to the second last topic of our chapter, that is concentration terms. First is molarity. It is the number of moles divided by volume in liters. Okay, we can further change the equation into number of moles. As we know, it is given weight by molecular weight. Now what is W2? 2 here, 2 and B, they both represent solute. Okay, so weight, given weight of solute divided by molecular weight of solute into whole volume of the solution. Okay, in liters. Okay, now if I want in milliliters, I will just take 1000 up. Okay, I will divide here by 1000, which means the same, this 1000 will go up. Okay, now coming to molality. Molality means what? It is the number of moles of solute, which is again N2, divided by W1, that is weight of solvent in kg. So it is W2 by MW2, that is given weight of solute divided by molecular weight of solute into 1000, because I took it in grams, divided by the given weight of solvent. Now coming to mole fraction. Okay, mole fraction, as we know, fraction word means the ratio. Okay, fraction of number of moles of one substance to another substance. Okay, so here psi A, this is represented by psi. Okay, represented by psi, that looks like letter X. Okay, so psi A is equal to, this is the mole fraction of A, which is mole fraction of solvent. Okay, first is solvent, after that it's solute. So first A solvent Mole fraction of solvent is equal to number of moles of solvent divided by total moles of the solution, that is solvent plus solute. Okay. So mole fraction of solute is number of moles of solute divided by the total number of moles in the whole solution. Coming to fourth one, which is normality. Normality means it is the number of gram equivalents of solute divided by volume. Now what is this gram equivalence or equivalent weight? This can be found for acids. If it is an acid, the gram equivalent weight can be found by molecular weight divided by basicity. Now what is basicity? Basicity is the number of replaceable H plus ions. Okay, you have to just remember the opposite. Basicity, basic substances have OH. So basicity means opposite, that is replaceable H plus ions. While that side for bases, equivalent weight is equal to molecular weight of that base divided by acidity, that is replaceable OH minus ions. Okay, for salts it depends upon the charge. Now we are done with the concentration terms. We go to the relationships between concentration terms, which is normality of M or normality of acids. Okay, so this is the relationship between normality and molarity. Okay, N and M. Capital M represents molarity R, whereas small m represents molality L. Okay, so first relationship is normality of acids can be written as molarity into basicity, that is replaceable H plus ions. Okay, while for bases it is molarity into replaceable OH minus ions. Okay, while for salts it is molarity into charge on the anion or cation. Okay, for oxidizing and reducing agents. Okay, so here oxidizing and reducing agents, as we learnt in the class 10. Okay, for them it is molarity into change in the oxidation number. Okay, now coming to relationship between molarity and the mass percentage. Okay, molarity and mass percentage are related as M is equal to 10 into X into D by M2. Now what are these terms? X is the mass percentage, okay, D is density, while M2 is the molecular mass of solute, second is solute, right? So now third relationship is relationship between small m and psi, that is molality L and X, that looks like X, that is mole fraction. Okay, so that is molality is equal to psi b by psi a into 1000 by MWA. Now what are these terms? MWA, first of all, A first is solvent, so it is molecular weight of solvent. Now here psi b means B second, again it's solute, second is solute. So mole fraction of solute divided by mole fraction of solvent into 1000 by molecular weight of solvent. So these were the concentration terms and the relationships. We have one more relationship, that is between molality and molarity. So the relation goes like molarity and molality. It is capital M, that is molarity, is equal to 1000. Why I have used 1000? Because for ml. Okay, volume in ml. Okay, so 1000 into small m, that is molality into D, density, divided by 1000 plus, remember this is 1000 plus, okay, 1000 plus m, that is again molality, into M2, that is molecular mass of solute. Remember 2 and B are for solute, while 1 and A are for solvent. Okay, so now this was the relationship between molality and molarity. Now coming to percentage purity. So let us assume a compound of 60 grams, and let me say that the actual compound, let us assume a solution of 60 grams, and in that the actual compound is 50 grams, okay, and impurities are for 10 grams. The whole compound comprises of 60 grams. Okay, So in this, what if I want to find how much is the compound is? Okay, so this will give me percentage purity. That is how much pure my compound is, or in that solution how much is the pure part in percentage. Okay, so that is weight of the compound divided by weight of the sample. Okay, into 100 of course, because it is percentage. Right, now we have some more relations, that is molarity in dilutions. In dilutions, the molarity of first into volume of first becomes equal to the molarity of second into volume of second substance. Okay, in chemical reactions it becomes molecular, that is molarity into volume by number of moles, that is N, is equal to first of second. Okay, first, the molarity of first into volume of first divided by number of moles of first substance is equal to the molarity of second substance into volume of second substance divided by number of moles of second substance. So with this we complete our chapter, that is some basic concepts of chemistry. You can check the notes in the community section of my channel.